Now please welcome to the stage, Theresa Benyo.
Thank you, and good morning. Oh, I feel like such a rock star this week. Honestly, I mean, it's been so much fun. I mean, between the production crew, Jerry, Ed, Marie, Mike, thank you so much for making us sound and look so good. And getting mentioned in a rap song, I mean, wow, that was just David Nagel taking my picture at the banquet. Oh, and now this morning, being in the same session as Ed Storms and Conrad Zursky. I mean, you're all so good for my ego. Oh my God. Well, hopefully my ego will stay intact after my presentation. Admittedly, I'm presenting a working theory. It's just in the initial stages. I welcome any and all feedback. After 33 years at NASA, I have a thick skin, so. All right, here's the outline of what I'm going to be talking about. We all know the first point, the gas cycling experiment, historic experiment by Gus Freilich. Wait, I gotta acknowledge my team here, acknowledge my team. Thank you so much. And Gus is participating virtually, so does Bob and Bruce Steinitz, so I'm gonna give a shout out to those guys. They've helped so much throughout this whole thing. And then after the experiment, I'll talk about the material analysis we completed. We did bulk and surface analysis, and then go into the theory based on electron screen fusion and fissioning. And then I'll wrap up with a summary. Okay, so you all probably know about this. I'm not gonna spend too much time on it other than Gus was the one that got me into this business. So it's all his fault. He had a small amount of funding to recreate an experiment he did in 1989. And I saw the highlight of that, and I said, hey, I want to get involved in that. So I've been involved with that ever since about 2012 or so. So anyway, you know, he saw rise in temperature, and but when we went to analyze the materials, we saw more than meets the eye, and I want to go through that. We did some bulk analysis of some of the materials, and this chart shows a unexposed piece of palladium, silver, and exposed, and all the elements that were detected in various concentrations of parts per million. And I'd like to note that things like chromium, manganese, and zinc were not detected in the unexposed sample, but they were afterwards, and zinc for really increased, or it really came up as a big component here. So, so we're like, wow, okay, there's something going on here, I wonder what. So we also did a lot of surface analysis with the scanning electron microscope, energy dispersive spectroscopy. We saw some areas of other elements besides palladium and silver, and they looked to be areas that were molten looking spots and craters, and this is just a sampling of what we saw. We have looked at dozens and dozens of sites on these tubes, both unexposed and exposed. So what to note here is that even though the system was kept under 425 degrees Celsius, you saw these areas that were like really melted, and palladium and silver melt at much higher temperatures than that. So what could be going on here? Then we, this is another area that we looked at. Well, first I went to the unexposed. Palladium, silver, like you think. And then traces of oxygen, silicon, iron, aluminum. Okay, that's reasonable. And then what we wanted to do with the exposed is also look at this under tough sim. So we had to create a trench and identify the spot that we wanted to look at under SEM and under TOF-SIMS. So we did a trench of gallium ions. So on a area that looked really interesting, and this is what it looked like under the color maps. So we have spots of copper, iron in approximately the same locations, maybe a little bit of chrome, and then kind of like a diffuse area of zinc. And then you'll see palladium and silver, there's some spots where they're not there. Okay, so under TOF-SIMS, here is the native material beforehand. We've got palladium, 4 of the, I think it's 5 natural isotopes. Here they're set out from highest to lowest, and it kind of goes along. More intense, 106, that's the highest abundance, and then 108, 105, 110. And then the same with silver, left and right, only 2 natural abundant isotopes there. So that's the native material. And then we saw all of this. We have chrome 54, nickel 58, both coppers, zinc, chrome, iron, a couple of the irons. So my team and I were just discussing this, like, how can this be? Where can this all come from? And this is another thing that I talked about on Monday, but I won't go into too many details, but we all probably know a little bit about electron screening, in fact, and that's, our main theory that we're testing and evolving and developing. So we've looked at it in terms of DD fusion, electron screening. However, if there's enough electron screening, could we do more than that? I want to give a little shout out to Dolan and Zapero, who we came across their work on heavy electrons and 3-body interactions, and Anthony gave a nice talk about that yesterday. But the more I looked at this, and my team as well, we talked about this, I'm like, well, this kind of looks like electron screening, at least to me. I just want to cite, I have their work cited there. And then Pines and Pines also have the electron screening that was on the previous slide. But, is it possible with this theory to have the deuteron completely consumed by either the palladium or silver? We started looking at that, and the list on the bottom there is the list of, possible interactions that follow all the conservation laws. And then on the lower right, there's a little picture that shows, how this could happen. And this would be the, consuming the proton with the Oppenheimer-Phillips process. Okay, then there was the fissioning aspect of it. Takahashi read a paper about their work and the photofissioning of palladium. So they observed pairs like iron and calcium and titanium and chrome, and I'm like, well, that's kind of similar to what we're seeing. They did it through electrolysis experiments. And so, is this possible? Can you do like a fusion and then a fission? When you fuse the deuteron with the palladium, would you get an unstable silver that would be unstable enough that it would break apart? And there's many possible pairs, again, observing all the laws of conservation. And we keyed in on pairs that we observed in our material analysis, like iron and titanium, manganese, chrome, and iron and chrome. Another aspect of this is the fission parameter. Now, a palladium, as you know, has a Z of 46. Silver is 47. And there is, there's a fission threshold of less than 10 MeV, despite, and there's the expected 50 MeV really is the actual, fission barrier height. But there's also something called this facility, well, that's probably not the way it's, facility relationship. And you can come up with this parameter that was developed by another researcher, so Z squared over A. And the theory is that if it's over 17, it's, it's able to fission an isotope. So for palladium, for example, it's over 20, same with silver. So, okay, well, this is potentially fissile. So, traditional fission, you've got the very high atomic numbers of uranium, plutonium, that's, pretty typical. So, we also, have to consider the binding energies and so on and so forth of that. But when you look at the OP reaction, Oppenheimer-Phillips reaction, you can see that there's going to be a kinetic energy of the proton, for instance, in this case, of 6 MeV, and also certain fusion reactions can create up to 14 MeV neutrons and 15 MeV protons. So there's a fair amount of kinetic energy that's in the area. But the other thing to note is that Palladium-105 isotope is kind of unique with palladium. It's got an oblate nucleus with a spin parity of 5 halves positive. So so with looking at the numbers, is it possible? Well, then when we started seeing the pairs that we're looking at, and then we're like, well, wait a minute. These don't kind of, really split out. We kind of looked at like, well, we see copper 65, for example. So what would pair with that? Well, it's like, well, it's not a stable pairing. It's something that would beta decay. And we found some instances where the beta decays would be very, very fast. So we started looking at, those kinds of pairs, and I spent many hours at the board looking at all kinds of different pairs that would be possible. And here's one, just a pair, with chromium and vanadium, with chrome 52 is the stable, and then vanadium 56 is the the unstable, and it would beta decay very quickly. You can see the decay chain there, and it would eventually get to iron 56. So, and we've seen iron and chrome in the same location on these samples. And again, a list of all kinds of other things. I want to point out chrome 52 and nickel 58, as you saw on previous slides, they're there. Also chrome 52 and iron 56, they're there in the top SIMS data. Again, you do the same thing with deuteron capture of silver, and these are just a few of the possible pairs that can come up. So in summary, we've observed these transmutations with deuterium gas cycling of the palladium-silver alloy with various material analysis techniques. We know the electron screening greatly reduces the Coulomb barrier, so that could very well facilitate the deuteron/proton capture of palladium or silver. And the capture results in an isotope to be unstable. However, the question that I still have is it unstable enough to cause fissioning, or is there some other yet unknown actor vehicle that assists with the fissioning of this unstable isotope? Still, so questions. Many fission pair possibilities exist. And of course, additional experiments, as always, with the working theory are needed to confirm this fusion-fission theory. So thank you for your attention, and I'll take some questions.
Yeah, very interesting work. So
Thanks.
We have a concern in our experiments. One is that whether transmutation occurs during the EDAX analysis itself. So we have done some experiments where we did EDAX and then top sims, but top sims is not all the time accessible. Have you switched and we see correlation between EDAX, WDX, and top sims, so that's good. But have you done this the other way around? Top sims first, and then EDAX, or do you see?
I don't think we have, but that's a good point. Yeah, we usually because we have a scanning electron microscope readily available here, and we don't have top sims readily available.
Case.
Yeah, so we usually do the SEM EDS
Do you also
first.
do WDS all the time?
No. Wait, I'm sorry. I'm not understanding the other method.
There's another spectroscopy.
Oh.
It's greater resolution, but takes more time to scan. So,
Yeah, and we haven't done that. No,
Okay.
we haven't done that.
All right. But is there any? I mean, do you have any thoughts on this? Is there transmutation during?
Well, yeah, as I talked about on Monday, we have done experiments with the scanning electron microscope using the electrons as a trigger for DD fusion. So it's not out of the realm of possibility, I don't think. Yeah.
All right.
That's possible.
Okay. Thank you.
All right, thank you. Oh, yeah, over here.
Thank you.
Thanks.
The criterion for calculating the possibility, or the probability, I should say, of fission for any charged pair of daughters is the Gamow suppression factor, because the energy of the fission reaction is only released when the two charged daughters are sufficiently separated. So there's a Coulomb barrier to tunnel through. And you can calculate pretty accurately what the probability of every individual fission reaction you can conjecture. And I think that should be the appropriate criterion for calculating the probabilities.
No, thank you. Thank you very much for that advice. I appreciate that. Yeah.
I'll give you my software, which does it automatically.
Oh, wonderful. Thank you.
And we have time for one more question.
All right.
My question is, if you discuss fission, you need high energy particles for that. So you can use some high energy particle from fusion experiment or fusion reactions, but they are so seldom. They are not frequent. Okay?
Yeah.
So this second order of reactions. So this is not so easy to explain it. Even the let's say screening energy will be higher. But the question is, maybe in the system, let's say deuteron plus heavy nucleus, the screening energy is really very, very high. And there are some indications for that. There is a group in Ljubljana in Slovenia, Professor Lipoglavsek, that measure screening energy in the opposite or inverse kinematic scheme. And they measure, instead of, let's say, 1 kV screening energies in the proton-induced or deuteron-induced reactions, 10 kV. So we don't understand it, because it is really very strange. So the question is, how strong is the dependence of the screening energies against atomic charge of included nuclei. So this is still open question. Maybe there's something.
Yeah. No, I agree. There's more. There's more to think about and consider with this.
They have sent now a very nice paper to Physics Letters B.
Yeah, I can't wait to see that. Yeah. Wonderful. Thanks.
Thank you very much, Theresa.
All right.